Today we're talking about some more intuition behind ResNets and trying to open up the black box of neural networks to see what's actually happening inside. So to do that, we're going to be looking at lost landscapes, and specifically how we visualize those lost landscapes and what they can tell us about the ease of optimizing our neural network weights. So we've gone over a lot of things that can affect how well our networks are optimized and how well they generalize. We've talked about changing batch sizes, changing our initialization of our weights, what kind of neural network topology or architecture we're using, learning rates, what types of optimizers, weight norms, and other types of regularization. And so today we're going to be looking at a paper that tries to kind of open up what the actual effect of each of those things is on the landscape of our loss. So this is kind of the key visualization from the paper. And on the left, we have, they call them both ResNet 56, but only the one on the right is actually ResNet. The one on the left is ResNet with the skip connections removed, so it's just a normal CNN. What do you notice looking at those lost surfaces? Yeah, Spencer, what do you think? Really easy to get caught in a local minimum on the one on the left. Absolutely, yeah. Yeah, I would totally agree. It looks like the right one is going to be much easier to optimize. Yeah, Dane, what do you think?
The left one kind of looks like Utah. So.
Oops. Yeah, I'd say, yeah, Southern Utah, some of that red rock for sure. Okay, so yeah, hopefully by the end of today, we will understand how they made these figures and why it isn't perhaps as straightforward as a problem as you might think. So here's another discussion question. So here we talked about ease of optimization, but now I'm going to ask a question about generalization based on sharpness or flatness of minima. So here we have two functions. We have a training loss function and a test loss function. And the idea generally in deep learning and machine learning is that we are trying to optimize our training loss function with the hypothesis that the test loss function will generally follow a similar pattern, and that by minimizing the training loss, we will also minimize the test loss. So here we have a training loss function in solid black and a test loss function in dashed red. And we have both a flat minimum and a sharp minimum that are, we're going to assume that these are the exact same loss, but one is, yeah, kind of shallow and the other is more sharp. What would you expect to see as far as the generalization of flat minimum versus a sharp minimum based on this picture? I'll let you think about that for a second. Which would you expect to generalize better? Yeah, Spencer? Exactly, yeah. So what Spencer's pointing out is that if we look at the minimizer for our training loss, it's pretty close to in terms of loss to a minimizer for the test loss, and that's in the shallow case. Whereas for the steep case, if we find the minimum of our train function and try to generalize the test function, the loss at that point is literally maximum loss. And so this is an illustrative example, but this is a hypothesis that people have had, is that flatter minima tend to generalize better than sharp minima. However, people have found that this is not always the case. And so this is one of the first things that the paper points out, is that you can get into trouble when making a visualization of a lost landscape like this, or like, so this is a 2D visualization of a lost landscape, and this is a one-dimensional visualization of a lost landscape. Obviously, so just to also back up a little bit, what we're doing here is we are taking two values of a single parameter, and we are interpolating between them, and then plotting the loss for every different value of that parameter. And same thing in this visualization, but we have two parameters that we are changing. Okay, however, there's an interesting nuance in ReLU-based networks. And that is that ReLU-based networks introduce what's called parameter scale invariance. I have a question for you. What happens if we take an input X, multiply it by a weight matrix W, and get an output, and also apply a ReLU? And then compare that to the following. We're going to take some constant and scale the output of our function, the output of our layer, by that constant. And then inside our ReLU, we will scale by the inverse of that constant. Can we simplify this bottom expression at all? What do you think? So for most non-linearities, the answer is no, we cannot normally pass a constant through our nonlinearity. Yeah, Tim, what do you think? Here, let me give you this. I like where you're going with this.
So my thought is that the 1 over a and the a will cancel out, because if a value is negative and you scale it, it will still be negative. And then if a value is positive and you scale it, it will still be positive. And so all the negatives will still go to 0. And then you just have a linear function on your positive values.
That is exactly right. Yeah. So it's a very important point, but a nuanced point. Yeah. So just to restate that, for the ReLU activation function, Tim is saying that if we have a negative value that ReLU is being applied to, then any scale of that negative value will still get mapped to 0. And then 1 over a times 0 is still 0. So negative values are 1 over a times r of a wx is equal to ReLU of wx. Then for positive values, ReLU is just the identity function. And so a times 1 over a equals 1, and we're unchanged. So yes, in fact, this simplifies to what we have in the top. Okay. So can you see how this observation could lead us to some potential issues when doing this, when we create this plot of our loss function with respect to parameters? It's not an easy question, but we'll see if you can get it.
I have no idea if this is right, but since like if we were changing how many dimensions we were doing it, would that essentially be like trying to scale the ReLU as we try to truncate it into like a one-dimensional model like this picture? And so when we do that, we think we're truncating the ReLU, like the loss function as well, but it actually doesn't because it's still equivalent or something, like it doesn't scale with that.
Yeah, so you're talking about different numbers of dimensions. I think you're on the right track. The key is that basically we can spread out or basically make minima wider or narrower based on the scale of our parameters. So we can have two networks that are exactly the same because with different values of weights, but with functionally the same behavior. And we can have that by scaling it up in one layer and then scaling down in the next layer. But if we plot the loss function with respect to the values of the weights of the network with large values, we're going to see our minima look much shallower than the minima of the network with small weights. And so that would make us think that the network with small weights has sharper minima and therefore worse generalization, when in reality they are the exact same network. So we're going to see, that's kind of a primer. We're going to see an example of this play out. Yeah, so I mentioned this before, but this is just to put this a little bit more precisely. This is how we make these plots. We're going to choose two sets of parameters, theta and theta prime. And we're going to trace out intermediate values of theta and theta prime. And there's a word for this that I've used before. Do you know what that word is? Where we have 1 minus alpha times theta plus alpha times theta prime, and then we change alpha. There's a vocab word that describes what this formula says. Any ideas? I heard parameterization. So yeah, it's definitely a parameterization. We call this interpolation because basically when alpha equals 0, we have completely theta, and when alpha equals 1, then we have 0 times theta plus 1 times theta prime. So it's a way of basically tracing out a line between these two theta values. Yeah, Dane? Yes, true. Yeah, this is linear interpolation. Good to clarify that. And so yeah, this is the same thing that we saw when we interpolated in latent space to visualize some of the transitions in our generative models. We would take one z vector and we would take another z vector, interpolate between them, and then plot the output generated image for each z vector. So same idea. We're interpolating between two parameter values, and then we're going to plot the loss of that parameter value. Okay, so this is a plot that is meant to illustrate the parameter scaling problem. So let's see if we can break this down. On the top row, we have plots related to a network trained with weight decay. Do we remember what weight decay is? Weight decay is the same as an L2 penalty on our network weights. So this is L2 regularization. Okay, so on the top, we have, we have no regularization on the top. And then on the bottom, we do have weight regularization. So weight decay equals 0 on the top, weight decay equals 0.0005 on the bottom. Okay, and then so first of all, what do you notice on, and then we're comparing two other things, and that is batch size. So in red, in these middle plots, we have batch size of 128. And in green on these plots, we have batch size of 8,000. So what do you notice about the top plot versus the bottom plot, the top middle versus the bottom middle? Also, oh yeah, and then so on the x-axis of these plots, we have number of training epochs. And on the y-axis, we are plotting the norm, the L2 norm of the weights. So yeah, I guess, first of all, let's just focus on the top middle. What do you notice about the, without weight decay, what do you notice about the norms of the weights for batch size 128 versus 8,000?
They get a lot bigger.
Totally. Yeah, they both, the magnitudes of the weights tend to increase. And then what do you notice about 128 compared to 8,000 batch size?
128 increases a lot more than 8,000 does.
Exactly. Yeah. So we are seeing this effect where small batches cause us to end up with weights with much larger magnitude. So hopefully you're starting to see where this might link into our visualization problem. We're ending up with two networks, one with small weights, one with large weights. And then, yeah, Drake, just to follow up on that. And then what do you see when we turn on weight decay of comparing the norm of the weights?
Well, it looks like the 8,000 one's bigger than the 200 one.
Yeah, exactly. So when we turn on weight decay, yeah, now we have the norm of the small batch size weights is smaller. We see that pattern flipped. Okay, so we understand what's happening with small batch versus large batch. So now we're going to try to tackle these plots on the left. And if you can understand these plots on the left, you will understand this paper. But it's it's very nuanced, the plots on the left. So we're going to see if we can tackle it. So on the plot, the plots here on the left, on the top we have, again, weight decay is 0. Bottom we have weight decay is turned on. And then at 0, we have the weights of a model trained with small batch. And at 1, we have at 1 we have the parameters of a model trained with large batches. And then we're going to interpolate between those weights. And yeah, so I guess first off, what do you see as far as the loss of, I guess the flatness of the loss of a model trained with small batch versus large batch? Which one has a flatter minimum? Yeah, so this first plot makes it look like training with a small batch gives us flatter minima, right? However, once we turn on weight decay, what happens? Now we still have small batch on the left, large batch on the right, but now which one seems like it has a flatter minima? The large batch now looks like it has a flatter minimum once we turn on weight decay. So based on what we understand about parameters, invariance to parameter scaling, why do you think this pattern flipped between the top and the bottom left diagrams? And give it a shot to Travis.
Yeah, complete shot in the dark. But does it have something to do with how, with like the dying, I can't remember what the term is, dying nodes with RailU? And so if you have a lot more parameters, then it's not dying, not as much dying, or I don't know, that shot in the dark.
It's an interesting thought. Yeah, this definitely reminds me a lot of the diagrams we were looking at when we were looking at dying RailUs and initialization and things like that. That's not actually quite the reason. So I'll tell you the reason, and it is because flatness of minima correlates best with L2 norm of weights. And so when we turned on normalization, the small batch went to having very large weights, to having very small weights. And so it went from having a very flat minimum to having a very sharp minimum. I'll say that one more time. What they observed is that turning on that the flatness of minima correlated far more than it correlated with generalization. It correlated with the size of the weights. And so when we didn't have regularization, we looked like we had a really flat minimum. And when we turned on regularization, it looked like we had a very sharp minimum. Okay. And so, yeah, that is parameter scale invariance for ReLU networks. And yeah, that's kind of the problem with visualizing these loss landscapes in a way that we're trying to glean insight from them.
Just really quickly, could you overcome some of this issue of a sharper minima by having just a lower learning rate?
Could you overcome the problem of a sharper minimum by having a lower learning rate? So it depends on what problem of sharper minimum you're talking about. So as far as generalization, a lower learning rate would not change anything. As far as optimizability, maybe. A lower learning rate could help us find the minima of sharp minima more easily. And so, yeah, it's interesting. You bring up a really good point that there are two things to think about when we're looking at the curvature of these loss surfaces. One is optimizability, and the other is generalization. Okay. So yeah, this is how we're going to make these 2D plots now. We're going to choose a center point, theta star, which will be 2 parameter values. It will be a vector of length 2. And then we will choose 2 random directions, delta and eta, and then basically scale alpha and beta in the same way that we did interpolation in 1 dimension. We're now going to do, this isn't interpolation, this is just, we're starting at a central point and then spreading out from that point in a radius by increasing alpha and beta from 0 to say 1. Okay, so this is the trick of this paper that's going to try to solve this parameter scale invariance problem. And it's called filter-wise normalization. And basically what you do is you take direction dij that came from selecting these random directions to vary our parameters in. And we're going to normalize that and scale by the norm of the parameter vector. And basically that normalizes out the scale of our parameters and basically gets rid of this parameter scaling problem so that we can trust the curvature of our loss visualizations once again. Okay, so yeah, this is another visualization that's trying to show the problem of trying to visualize loss landscapes without this normalization. So we're comparing A and E and C and G. So, and we're looking at the flatness of each of these minimizers as well as the error rate. So what do you notice as like A versus E? Is A flat, which has a smoother loss surface, A or E? A has a smoother loss surface, and which has a lower error? E, right? E has an error rate of 6% versus A has an error rate of 7%. So in this case, it makes it look like a narrow narrow minimum, a sharp minimum, has better generalization. But now let's pop over to C versus G. Which one looks flatter, C versus G? Yes. Oh, wait. Yeah, and then which one has a lower test error? Also C. So this is meant to show that in one case, sharper minimum correlated with lower test error, and in the other case, flatter minimum correlated with lower test error. So again, showing the problem of training these doing these visualizations without normalization. Have we beat that horse to death yet? Okay, good. Any questions on that? Okay. All right, so yeah, I want to make sure that I'm giving you the right description for this slide. Let me check my notes quick. Okay, yeah, so these are with the normalization now. Yep. Okay. All right, so we have had this, so to review, we had this intuition about, we think that flatter minima should generalize better, but then we saw some cases where it wasn't, but we explained those cases by the fact that there's this problem with normalization in visualizing these loss landscapes. Now we have turned on normalization. And so what do you notice now about the correlation of flatness of minimizers with test error rates? Let's first look at this top row. These are 1D loss landscape visualizations. What in here look like our flattest minima out of A through D? A and C. Yep. And they have error rates of 7.37 and 6.0. And then what look like our sharpest minima? Probably B and D, right? And those have an error rates of 11% and 10% respectively. And so you can see like there's a very close correlation now with flatness of minima and generalization error. So are we convinced that this normalization thing is a good idea? Maybe. We'll see. At least in one case, it looks like it's doing a pretty good job of helping our flatness of minima correlate with test error. Let's take a look at the second row. So second row is the same thing, the same networks, but just 2D loss visualizations. Just to kind of calibrate what we're looking at here, these are contour maps where lines that are closer together means that they are steeper, and lines that are spread farther apart mean that it's flatter. So out of these four, which are the steepest? Which ones? F and H, exactly. Yep. And then the shallowest are E and G, right? Yeah, and again, we can see similar, I mean, they're the same error rates, but again, we can see what is obviously the flattest has the lowest error rate. And as we get to be steeper and steeper, you can see there's a very close correlation with test error. Okay, any questions or comments? All right. Okay, so this is where it kind of gets interesting. And so now that we have a trustworthy loss landscape visualization method, we are going to compare ResNets to ResNets with no skip connections. I don't know why they're calling them ResNets because they aren't ResNets anymore. They're just normal CNNs. But yeah, so on the bottom, we have normal CNNs, and on the top, we have ResNets. And what do you notice about the smoothness and or shallowness or sharpness of these lost landscapes? Yeah, definitely. So ResNets are definitely looking a lot smoother. Yeah, Max. Yeah. Yeah, exactly. I mean, and you can see that another kind of interesting thing to look at is what do you notice about the smoothness of these lost landscapes as we go from left to right? As we go, and I'll tell you, as we go from left to right, we're changing the number of layers. So on the left, we have 20 layers. The middle, we have 56 layers. On the right, we have 110 layers. What do you notice about the smoothness of the landscapes as you go from left to right? Yeah, at least in the case of the normal CNN, they become a lot messier. And so we can see, and this seems to make sense and correlate with our error rates. When we only have 20 layers, these residual connections don't seem to make a huge difference in either the smoothness of the landscape or in our error rates. But as we get deeper, we can see that adding these skip connections helps us preserve the smoothness of this landscape and also see an improvement in error rate. Yeah.
A question I had about the paper was when we're changing parameters in a ResNet, there could be like millions of parameters. So we're in like a huge dimensional space when we're minimizing the loss. So I didn't quite understand how they put these lost landscapes into just 2 dimensions. You could maybe explain that a little bit.
Great question. So yeah, the question is how did we get into a 2-dimensional loss visualization from a potentially millions or billions of parameter network? And the answer is we picked 2 parameters randomly. Yeah, and the hope is that by doing so, we get by seeing how the loss landscape varies as a function of those parameters, we can perhaps generalize that to it's probably doing similar things with respect to other parameters as far as smoothness. However, that brings up a really interesting question of like, how would the smoothness of the loss landscape of the earlier layers of the network compared to the smoothness of the landscape for the last parameters in the network? I might venture to, well, actually, yeah, that's a good question. So let's say we're taking a 110 layer ResNet with no skip connections. And we are looking at the very last parameters of the network. So right before the loss function. Would you expect the loss landscape for those parameters to be smoother or more jagged compared to the one we see here? I think I heard a whisper. Anyone we haven't heard from yet today? So to repeat the question is if we have 110 layer CNN without normalization, how do you expect and then this visualization was made by taking 2 random parameters from the network. What do you think would happen if we took 2 parameters from the very last layer right before the loss function? How do you expect the loss landscape to compare for parameters late in the network?
I would guess it would be smoother because you don't have as much of an opportunity for error to propagate back.
Yeah, Spencer thinks it would be smoother because you have less of a chain rule of derivatives. Anyone want to take a different position? I think I tend to agree with Spencer. I think that's what I would expect, is that you probably see a smoother loss landscape for the later layers of the network and a more jagged one for some of these early parameters that the gradient has to travel a long ways towards in order to optimize. Okay. This is another interesting visualization. So on the left, we have a normal CNN. And then in the middle, we have what's called a dense net. So this is something we mentioned at the end of last class based on Drake's question. And this is what a dense net looks like. On the right-hand side, we have the architecture of a dense net. What do you notice about the skip connections of a dense net compared to a ResNet? Does this architecture look different from the ResNet architecture that we saw? I'm seeing some nodding heads. Exactly, you have connections going everywhere instead of just to the next. So this first layer, instead of just being connected between the first layer and the second layer, it's being connected between the first and the second, first and the third, the first and the fourth, and then the first all the way to the end. And then same with all of these other layers, they are connected to all of the layers that follow. And so that's called a dense net architecture. And you can see, like, can you imagine a better loss landscape to optimize? That's pretty much as convex as you get. So that's pretty good. And I'm pretty sure with that dense net, they've trained networks up to 1,000 layers. So yeah, so last class we talked about some kind of like theoretical ideas of why we thought that ResNets and these identity skip connections were helpful. And now we're seeing some kind of empirical evidence of like that these theoretical ideas are actually very effective on smoothing out, and perhaps why they're effective by smoothing out the loss landscape. Any questions or comments on DenseNet? Okay. So this is an interesting visualization of wide versus thin networks. So when we're talking about wide networks, if we're talking about convolutional networks, that means we have a lot of filters in each layer. Versus thin networks would be just a few filters in each layer, but many, many layers. And so in this diagram, we have from left to right, we have the number of filters. And from top to bottom, we have with skip connections and without skip connections. What do you notice as far as as far as patterns in this diagram? Yeah, Daniel.
So generally wider networks just have less, more even loss landscapes.
Definitely. Yeah. So it seems like wider networks tend to have flatter minima. And then top to bottom, we see the same trend that we've seen before. And so we've seen a couple of different visualizations of different variations on networks and how they affect the smoothness of minima. What are some other things, like if you were to make another diagram for this paper, what is something that you might be interested in its effect on the smoothness of the loss landscape?
I'd be curious to see how different initialization strategies affect the shape.
Totally. Yeah, that'd be very interesting to see. Yeah, Michael, what do you think?
I would be interested in how, in the dense net, how the period of the connections affect the loss landscape.
What do you mean by the period? Just like how many you're skipping at a time, or? Gotcha. Yeah. Interesting. Yeah. Yeah, these are some good ideas. And so these are totally the types of visualizations that you could make. It's not that hard. Like we saw the math of how to do it. You can go into the paper more if you want to learn how to do this. So these would be some really interesting visualizations that you could make for your final project. And also if you wanted to, investigate the effect of different variations on your network architecture, if you wanted to evaluate their perhaps effect on the smoothness of the loss surface, those could be some really interesting experiments to run. So yeah, I think that's all we have for today on loss landscape visualization. Any questions? Comments? Yeah, Dane. The earlier which visualization? Sure. Yeah, we can take a look at that one. Yeah, because honestly, that first thing that we looked at was probably the hardest diagram in this lecture, and we were the least prepared for it. So let's see if we can understand this again. So on the left hand, we're trying to understand the left-hand side of these, right? And so at 0, we have the parameters from training with large batches. And at 1, we have the parameters from training with large batches. And on top, we have training without regularization. And on the bottom, we have training with regularization. Yeah, weight decay is weight regularization. Yep. And so we saw that in the top left, the lack of weight decay caused the small batch size to end up with much larger weights, which spread out which basically made the minimum of the small batch size look flatter than it actually was. Whereas when we turned on weight regularization, the large batch size ended up with larger weights. And so the large batch looked like it had a flatter minimum. Yeah, and so the whole idea of the paper was we're going to introduce this normalization that gets rid of the scale invariance of our loss function and allows us to get a more realistic look at how different things like different batch sizes affect the sharpness of our minima. And we saw that after we did that, we were able to get much stronger correlation between flatness of minima and error rates. Okay, this is kind of it's a very nuanced issue that we discussed today, but I think it's an interesting one. And yeah, it's good to think precisely and adversarially when you're whenever you're trying to do something like this, because like if I had thought to look at the smoothness of my loss landscape, I probably would not have thought to normalize with respect to scale of parameters or things like that. So it's nice that there are people out there who did think of that nuance and were able to help us out with these visualizations. All right, have a good weekend.